Work and Energy, Grade 9 Science Chapter 11. Hello and welcome to isaykids, gateway to learning and fun. Subscribe now for an enriching experience. All living beings need food. Living beings have to perform several basic activities to survive. We call such activities life processes. The energy for these processes comes from food. We need energy for other activities like playing, singing, reading, writing, thinking, jumping, cycling, and running. Activities that as learners require more energy. Animals too get engaged in activities. For example, they may jump and run. They have to fight, move away from enemies, find food, and find a safe place to live. Also, we engage some animals to lift weights, carry loads, pull carts, or plow fields. All such activities require energy. Think of machines. What do they need for their working? Work. There is a difference in the way we use the term work in day-to-day life and the way we use it in science. Kiara is preparing for her examinations. She spends a lot of time in studies. She reads books, draws diagrams, organizes her thoughts, collects question papers, attends classes, discusses problems with her friends, and performs experiments. She expends a lot of energy on these activities. In common parlance, she is working hard. All this hard work may involve very little work if we go by the scientific definition of work. You are working hard to push a huge rock. Let us say the rock does not move despite all the effort. You get completely exhausted. However, you have not done any work on the rock as there is no displacement of the rock. You stand still for a few minutes with a heavy load on your head. You obviously get tired. You have exerted yourself and have spent quite a bit of your energy. Are you doing work on the load? The way we understand the term work in science, work is not done. You climb up the steps of a staircase and reach the second floor of a building just to see the landscape from there. You may even climb up a tall tree. If we apply the scientific definition, these activities involve a lot of work. In day-to-day life, we consider any useful physical or mental labor as work. Activities like playing in a field, talking with friends, humming a tune, watching a movie, attending a function are sometimes not considered to be work. What constitutes work depends on the way we define it. We use and define the term work differently in science. To understand the way we view work and define work from the point of view of science, let us consider some situations. Push a pebble lying on a surface. The pebble moves through a distance. You exerted a force on the pebble and the pebble got displaced. In this situation, work is done. A girl pushes a trolley and the trolley moves through a distance. The girl has exerted a force on the trolley and it is displaced. Therefore, work is done. Lift a book through a height. To do this, you must apply a force. The book rises up. There is a force applied on the book and the book has moved. Hence, work is done. A closer look at the above situations reveal that two conditions need to be satisfied for work to be done. A force should act on an object and the object must be displaced. If any one of the above conditions does not exist, work is not done. This is the way we view work in science. A bullock is pulling a cart. The cart moves. There is a force on the cart and the cart has moved. Do you think that work is done in this situation? Work done by a constant force. Consider the case when the force is acting in the direction of displacement. Let a constant force F act on an object. Let the object be displaced through a distance s in the direction of the force. Let W be the work done. We define work to be equal to the product of the force and displacement. Work done is equal to force into displacement. Thus, work done by a force acting on an object is equal to the magnitude of the force multiplied by the distance moved in the direction of the force. Work has only magnitude and no direction. If force is 1 Newton and displacement is 1 meter, then the work done by the force will be 1 Newton meter. Here, the unit of work is Newton meter or joule. Thus, 1 joule is the amount of work done on an object when a force of 1 Newton displaces it by 1 meter along the line of action of force. We know that work done is equal to force into displacement. What do you think is the work done when the force on the object is 0? What would be the work done when the displacement of the object is 0? Let us know in the comment section below. Now consider this example. A force of 5 Newton is acting on an object. The object is displaced through 2 meters in the direction of the force. If the force acts on the object all through the displacement, then work done is 5 into 2, which is 10 Newton meter or 10 joules. Considering another example where a force of 7 Newton acts on an object. The displacement is 8 meter in the direction of the force. What is the work done in this case? It will be force into displacement, which is 7 times 8, which gives us 56 joules. Now consider another situation in which the force and the displacement are in the same direction. A girl pulling a toy car parallel to the ground, as shown here. The girl has exerted a force in the direction of displacement of the car. In this situation, the work done will be equal to the product of the force and displacement. In such situations, the work done by the force is taken as positive. Consider a situation in which an object is moving with a uniform velocity along a particular direction. Now, a retarding force F is applied in the opposite direction. That is, the angle between the two directions is 180 degrees. Let the object stop after a displacement S. In such a situation, the work done by the force F is taken as negative and denoted by the minus sign. The work done by the force is F into minus S. Thus, the work done by a force can either be positive or negative. Lift an object up. Work is done by the force exerted by you on the object. The object moves upwards. The force you exerted is in the direction of displacement. However, there is the force of gravity acting on the object. Now, which one of these forces is doing positive work and which one is doing negative work? The work done by the force of gravity is negative because the force of gravity acts in the downward direction, that is, in the opposite direction of the displacement of the object. Work done is negative when the force acts opposite to the direction of displacement. It is positive when the force is in the direction of displacement. A porter lifts a luggage of 15 kg from the ground and puts it on his head 1.5 meter above the ground. Let's calculate the work done by him on the luggage. The mass of luggage is 15 kg and displacement is 1.5 meters. Work done is F into S. Now force is mg So mg would be 15 into 10 meters per second square, and work done would be 150 into 1.5, which gives us 225 Newton meter or 225 joules. Before we start with the next topic, which is energy, let's do a quick recap of the previous topic, work. When do we say that the work is done? The work is said to be done when force is applied on an object moves through a distance in the direction of the application of force. Let's consider one more example. A pair of bullocks exerts a force on 140 Newton on a plow. The field being plowed is 15 meters long. How much work is done in plowing the length of the field? Work done by the bullocks is given by the expression F into D, where applied force is 140 Newton, displacement is 15 meter, W is 140 into 15, which gives us 2100 joules. Hence, 2100 joules of labor is finished in tilling the length of the sector. Next is energy. Life is impossible without energy. The demand for energy is ever increasing. Where do we get energy from? The sun is the biggest natural source of energy to us. Many of our energy sources are derived from the sun. We can also get energy from the nuclei of atoms, the interior of the earth, and the tides. Can you think of other sources of energy? Well, biofuel energy, hydropower, geothermal energy, nuclear energy, and wind energy are some other sources of energy. The word energy is very often used in our daily life, but in science we give it a definite and precise meaning. Let us consider the following examples. When a fast-moving cricket ball hits a stationary wicket, the wicket is thrown away. Similarly, an object when raised to a certain height gets the capability to do work. You must have seen that when a raised hammer falls on a nail placed on a piece of wood, it drives the nail into the wood. We have also observed children binding a toy, such as a toy car, and when the toy is placed on the floor, it starts moving. When a balloon is filled with air and we press it, we notice a change in its shape. As long as we press it gently, it can come back to its original shape when the force is withdrawn. However, if we press the balloon hard, it can even explode, producing a blasting sound. In all these examples, the objects acquire through different means the capability of doing work. An object having a capability to do work is said to possess energy. The object which does the work loses energy, and the object on which the work is done gains energy. How does an object with energy do work? An object that possesses energy can exert a force on another object. When this happens, energy is transferred from the former to the latter. The second object may move as it receives energy and therefore do some work. Thus, the first object had a capacity to do work. This implies that an object that possesses energy can do work. The energy possessed by an object is thus measured in terms of its capacity of doing work. The unit of energy is therefore the same as that of work, that is, joule. 1 joule is the energy required to do 1 joule of work. Sometimes a larger unit of energy called kilojoule is used. 1 kilojoule equals 1000 joules. If something is capable of doing work, then that entity is assumed to have energy, be it in any form. For example, a heat is a form of energy which makes the air particles move. Similarly, sound is a form of energy which makes them vibrate. Forms of energy. The various forms of energy include mechanical energy, which is a combination of potential energy and kinetic energy, heat energy, chemical energy, electrical energy, and light energy. James Prescott Jewel was an outstanding British physicist. He is best known for his research in electricity and thermodynamics. Amongst other things, he formulated a law for the heating effect of electric current. He also verified experimentally the law of conservation of energy and discovered the value of the mechanical equivalent of heat. The unit of energy and work, called joule, is named after him. When you stretch a rubber band, you transfer energy to it. The energy transferred to the band is its potential energy. You do work while winding the key of toy car. The energy transferred to the spring inside is stored as potential energy. The energy transferred to an object is stored as potential energy if it is not used to cause a change in the velocity or speed of the object. We can also say that the potential energy possessed by the object is the energy present in it by virtue of its position or configuration. When an arrow is released after stretching the string of a bow, the potential energy stored in the bow due to the change of shape is used in the form of kinetic energy in throwing off the arrow. Potential energy of an object at a height. An object increases its energy when raised through a height. This is because work is done on it against gravity while it is being raised. The energy present in such an object is the gravitational potential energy. The gravitational potential energy of an object at a point above the ground is defined as the work done in raising it from the ground to that point against gravity. It is easy to arrive at an expression for the gravitational potential energy of an object at a height. Consider an object of mass m. Let it be raised through a height h from the ground. A force is required to do this. The minimum force required to raise the object is equal to the weight of the object, which is m into g. The object gains energy equal to the work done on it. Let the work done on the object against gravity be W. That is, W equals force into displacement, which is mg into h. Since work done on the object is equal to mgh, an energy equal to mgh units is gained by the object. This is the potential energy. The potential energy of an object at a height depends on the ground level or the zero level you choose. An object in a given position can have a certain potential energy with respect to one level and a different value of potential energy with respect to another level. It is useful to know that the work done by gravity depends on the difference in vertical heights of the initial and final positions of the object and not on the path along which the object is moved. Figure here shows a case where a block is raised from position A to B by taking two different paths. Let the height AB be h. In both the situations, the work done on the object is mgh. Find the energy possessed by an object of mass 10 kg when it is at a height of 6 meters above the ground. We are given that g is 9.8 meters per second square. The mass of the object is 10 kg. Displacement is height, which is 6 meter, and the acceleration due to gravity is 9.8 meters per second square. Now we know that potential energy is mgh, so it will be 10 into 9.8 into 6, which gives us 588 joules. Thus, the potential energy is 588 joules. An object of mass 12 kg at a certain height above the ground. If the potential energy of the object is 480 joules, find the height at which the object is with respect to the ground. Given g is 10 meters per second square. Mass of the object is 12 kg, potential energy is given as 480 joules. Now potential energy is mgh. We are given m as 12 and g as 10. So height would be 4 meter. The object is at the height of 4 meter. Are various energy forms interconvertible? Can we convert energy from one form to another? We find in nature a number of instances of conversion of energy from one form to another. Green plants convert solar energy to food. Sunlight also aids in the movement of air. Heat energy from the sun aids in the formation of fuels such as coal and petroleum. The water cycle is driven primarily by the energy from the sun. Law of conservation of energy. According to the law of conservation of energy, energy can only be converted from one form to another. It can neither be created nor destroyed. The total energy before and after the transformation remains the same. The law of conservation of energy is valid in all situations and for all kinds of transformations. Consider a simple example. Let an object of mass m be made to fall freely from a height h. At the start, the potential energy is mgh and kinetic energy is 0. If you know why is the kinetic energy 0, because its velocity is 0. The total energy of the object is thus mgh. As it falls, its potential energy will change into kinetic energy. If v is the velocity of the object at a given instant, the kinetic energy would be half mv square. As the fall of the object continues, the potential energy would decrease while the kinetic energy would increase. When the object is about to reach the ground, h is 0 and v will be the highest. Therefore, the kinetic energy would be the largest and potential energy the least. However, the sum of the potential energy and kinetic energy of the object would be same at all points. That is, potential energy plus kinetic energy is constant. The sum of kinetic energy and potential energy of an object is its total mechanical energy. We find that during the free fall of the object, the decrease in potential energy at any point in its path appears as an equal amount of increase in kinetic energy. Here, the effect of air resistance on the motion of the object has been ignored. There is thus a continual transformation of gravitational potential energy into kinetic energy. Now, let's perform an interesting activity. What would have happened if nature had not allowed the transformation of energy? If the transformation of energy would have not been allowed by the nature, then many of the processes would have failed to occur. Simple things like cooking food would not have been possible. Similarly, growth in the body would have been hampered as the stored food would not have been converted. Rate of doing work. Do all of us work at the same rate? Do machines consume or transfer energy at the same rate? Agents that transfer energy do work at different rates. A stronger person may do certain work in relatively less time. A more powerful vehicle would complete a journey in a shorter time than a less powerful one. We talk of the power of machines like motorbikes and motor cars. The speed with which these vehicles change energy or do work is a basis for their classification. Power measures the speed of work done, that is, how fast or slow work is done. Power is defined as the rate of doing work or the rate of transfer of energy. If an agent does a work W in time T, then power is given by work upon time. The unit of power is watt in honor of James Watt, having the symbol W. 1 watt is the power of an agent which does work at the rate of 1 joule per second. We can also say that power is 1 watt when the rate of consumption of energy is 1 joules per second. We express larger rates of energy transfer in kilowatts. 1 kilowatt is equal to 1000 watts. We can also say that 1 kilowatt is equal to 1000 joules per second. The power of an agent may vary with time. This means that the agent may be doing work at different rates at different intervals of time. Therefore, the concept of average power is useful. We obtain average power by dividing the total energy consumed by the total time taken. Let's discuss this with an example. Two girls, each of weight 400 Newton, climb up a rope through a height of 8 meters. We name one of the girls A and the other B. Girl A takes 20 seconds while B takes 50 seconds to accomplish this task. What is the power expended by each girl? Power expended by girl A. Her weight is 400 newtons and displacement is 8 meters. Time taken is 20 seconds. So the power expended by her would be 400 into 8 by 20, which gives us 160 watts. Power expended by girl B. Weight is again 400 newtons, displacement is 8 meters and time taken is 50 seconds. So the power expended would be 400 times 8 by 50, which gives us 64 watts. Thus, the power expended by girl is 160 watts and by B is 64 watts. A boy of mass 50 kg runs up a staircase of 45 steps in 9 seconds. If the height of each step is 15 cm, find his power. Weight of the boy is mg, which is 50 into 10, which gives us 500 newtons. Height is 45 into 15 by 100, which gives us 6.75 meters. Time taken to climb will be 9 seconds. Now power is work done by time taken. So it will be mgh by t, which gives us 500 times 6.75 by 9. Thus, power is 375 watts. Let's see one more example. A lamp consumes 1000 joules of electrical energy in 10 seconds. What is its power? Now E is 1000 joules, T is 10 seconds. Power would be E upon T. It will be 100 watts. Commercial unit of energy. The unit joule is too small and hence is inconvenient to express large quantities of energy. We use a bigger unit of energy called kilowatt hour. Now what is 1 kilowatt hour? Let us say we have a machine that uses 1000 joules of energy every second. If this machine is used continuously for 1 hour, it will consume 1 kilowatt hour of energy. Thus, 1 kilowatt hour is the energy used in 1 hour at the rate of 1000 joules per second. 1 kilowatt hour is 1 kilowatt into 1 hour, which is 1000 watt into 3600 seconds. So 1 kilowatt hour is 3.6 into 10 raised to the power 6 joules. The energy used in households, industries, and commercial establishments are usually expressed in kilowatt hour. For example, electrical energy used during a month is expressed in terms of units. Here, 1 unit means 1 kilowatt hour. An electrical bulb of 60 watt is used for 6 hours per day. Calculate the units of energy consumed in 1 day by the bulb. Power of electric bulb is 60 watt, which is 0.06 kilowatt. Time used is 6 hours. Energy is power into time taken. So it comes out to be 0.36 units. That's it for today. Check back soon, we'll be uploading more. Have a great day. Bye-bye.